Good afternoon. My name is Julian Moraro. And in this talk, I'll describe Egalitarian Paxos, which is a new state machine replication protocol based on Paxos. This is joint work with my advisor at Carnegie Mellon University, David Anderson, and with Michael Kaminsky from Intel Labs. Redundancy is critical for fault tolerance. And that is true in computing as in any other field. In distributed computing, this approach is called state machine replication. And what it comes down to is having a set of distributed processes that execute the same commands in the same order. And if we can get them to do that, then they will transition through the same sequence of states. And even if some of them fail, the remaining ones will be able to handle client queries and commands just as the failed ones would have. And the analogy here is with vehicles. If they start in the same point and follow the same directions, they will reach the same destination. And in practice, there are many ways to implement state machine replication, ranging from simple primary backup protocols to more complex protocols, such as Paxos and Byzantine fault tolerance. The reason why Paxos is popular is because it's a fast protocol, and it does not depend on external failure detectors, which means that it has very fast failover, or in other words, very high availability. And Paxos is important. For example, in local area clusters, systems such as Chubby, Boxwood, Smarter implement Paxos. Zookeeper uses a protocol very similar to Paxos. And they use Paxos for operations such as distributed synchronization, resource discovery, and even on the data path. And because we build bigger and bigger clusters, there is increasing pressure on these implementations of Paxos to have both high throughput and high availability. We also use Paxos in the wide area because we access the same databases synchronously from different continents. So we want to bring that data closer to clients. And we also want to be able to tolerate full data center outages. But because distances in this setting are so large, any inefficiency in unnecessary message delays to commit are going to have a very high impact on usability. So low latency is critical in this setting. Before I can describe our solution, it is useful to go through a quick overview of the Paxos protocol. So at its core, Paxos is an agreement protocol used by a set of distributed processes to agree on one thing. It tolerates F failures with 2F plus 1 total replicas, and that's optimal because we don't depend on external failure detectors. It handles only non-Byzantine failures, which is to say that machines can fail to reply for an indefinite amount of time, but they will not reply in ways that do not conform to the protocol. And finally, for Paxos to be safe, there's no synchronicity assumption that we have to make about communication. So how do we use Paxos to order commands? And this is an example. Let's say we have 3 replicas. And this is the replicated state, which is a sequence of pre-ordered command slots. They're initially empty. And clients submit commands to these replicas. And the replicas will contend for these slots. And they will do so by running Paxos. As a result of running Paxos, only one of them will win. The other ones will know which one that is, and they will choose a different slot. And so on until a contiguous sequence of slots has been filled, at which point every replica can independently execute the same commands in the same order. So the takeaways here are that with Paxos, we choose commands independently for each slot, and order arises as a way we use the protocol to contend for these pre-ordered slots. Order is not something that the protocol deals with explicitly. It's also important to note that it takes at least 2 round trips to commit a command. One to take ownership of a slot, and the second one to actually propose the command. If there are dueling leaders, it will take more than 2 round trips. And because of this inefficiency, most practical implementations actually implement Multi-Paxos. In Multi-Paxos, there is a designated stable leader replica, which is the default owner of all the slots. And because it is a default owner of all the slots, all the clients will communicate with only this replica, and it will be able to get these commands committed in just 1 round trip. And this is great for latency. It's also very good for throughput. It takes just 1 round trip to commit a command, but we have this potential performance bottleneck, which is the single leader, and also an availability bottleneck, because if the leader fails, there's going to be a period of unavailability until a new leader is elected. So the question is, can we have it all? And this is the question that motivated our research. Can we have the nice throughput and low latency of Multi-Paxos, but without losing the constant availability of Paxos? Can we also distribute load evenly across all replicas so that we have high throughput? It will also be nice to be able to avoid those replicas that experience high load. So we want to use the fastest replicas at any given point to commit commands. And for low latency in the wide area, we want to be able to commit commands after talking to just the closest replicas. And Paxos has these properties, but it doesn't have high performance because of the 2 round trips. Multi-Paxos solves that problem, but it loses all the other properties in the process. In contrast, Egalitarian Paxos has all these properties and implements them efficiently, so much so that it has higher performance than Multi-Paxos. And EPaxos is all about ordering. So we've seen that previous approaches for ordering included contending for slots, and this is canonical Paxos. One replica decides, and this is Multi-Paxos, but also other variants of Paxos, like fast Paxos and generalized Paxos. And another approach from a more recent version of Paxos called Mencius, where replicas take turn round robin in proposing commands. So it is pre-established that replica 1 is the default leader over every 3rd slot starting at 1. Replica 2 is the default leader over every 3rd slot starting at 2, and so on. We've seen the problems with the first 2 approaches. The problem with the 3rd is that a replica cannot commit a command until it has learned what has happened in the previous slots owned by all the other replicas. So as a result, Mencius runs at the speed of the slowest replica. So by contrast, in EPaxos, we do something very different. Instead of having this linear sequence, or this linear command slot space, we split it into as many subspaces as there are replicas. And we give default ownership to each replica over one of these subspaces. Clients can choose any replica to submit a command, and those replicas will get those commands committed in a slot belonging to their own subspace. You can think about it as you can think of the replicated state as this 2-dimensional array. And this is great because replicas no longer contend for slots, but it's no longer clear how are we going to order these commands, right? It's no longer clear whether 2.2 should come before or after 3.1. And the way we do it is, in the process of voting for commands, replicas also attach ordering constraints to these commands. And these ordering constraints say that, for example, B has an ordering dependency on A and should come after A, should be ordered after A. And when all these commands have been committed, all non-faulty replicas will have the same commands in the same slots with the same ordering constraints. So they will be able to independently analyze these constraints and reach the same ordering decision. This is good because we get load balancing, we get good load balancing. Every replica can be a command leader. But also, we have the flexibility to choose any quorum of replicas to commit a command. And in particular, this will allow us to avoid slow replicas or replicas that are far away. And to go into a bit more detail, this is the EPaxos commit protocol is a time sequence diagram with 5 replicas and time flows from left to right. And let's say that command A has been submitted to replica 1. Replica 1 sends a pre-accept message to a majority of replicas, that is itself and 2 other replicas, R2 and R3, saying that A depends on nothing because it hasn't seen any other command at this point. And R2 and R3 agree. And because of that, R1 can commit locally and then asynchronously notify everyone else. And let's say that at about the same time, command B has been proposed to replica R5. R5 says B depends on nothing. R4 agrees because it hasn't seen A. But R3 has pre-accepted A, so it says B should depend on A. Because R3 and R4 disagreed, R5 has to run a second round of communication where it tells a majority of replicas what are the final ordering constraints for command B. B depends on A. And the replicas don't have to update these ordering constraints, they just have to acknowledge, at which point R5 commits B locally and notifies everyone asynchronously. And one last example, let's say C is proposed to R1. R1 hasn't seen the commit for B at this point, says C depends only on A. But of course, R2 and R3 have seen the commit for B, and they say C depends on both A and B. And because R2 and R3 agreed, R1 can commit locally and notify everyone asynchronously. So a simple analysis of this protocol, a quick analysis, will show you that it takes 1 round trip to commit a command for non-concurrent commands, and at most 2 round trips to commit a command when commands are concurrent. And this seems bad because we want our system to be able to handle many concurrent commands. To our rescue comes this observation made before us by generalized Paxos and generic broadcast protocols, which is that we don't actually have to consistently order every command with respect to every other command, just those commands that interfere. And a simple way to think of this is commands that refer to the same state. So applying this, we will be able to commit a command after just one round trip for those commands that are either non-concurrent or are concurrent but don't interfere. And we will have to take 2 round trips for some of the commands that are both concurrent and interfere. And it turns out that in practice, it is rare that commands are concurrent and interfere. So most of the time, we'll be able to commit commands after just 1 round trip. But the next logical question is it easy to determine whether 2 commands interfere before we execute them? Because remember, we first have to order these commands, and only then can we execute them. Well, the answer is application specific. For NoSQL systems that are variations of key value stores, it is easy to infer interference because we can just look at the operation key. If the keys for 2 operations match, then those operations interfere. If not, they don't. Another approach is to have the programmer specify interference explicitly. And this is similar to what Google App Engine requires of developers. And finally, even for more complex databases like relational databases, it turns out that it's possible to infer interference because most transactions executed in OLTP workloads are simple enough that we can analyze them before execution and we can tell exactly which rows in which tables they will touch. The remaining few transactions for which we cannot do that, it is safe to assume that they interfere with everything else. So we've committed these commands. How do we execute them? Let's say that we have 5 commands, and this is how a dependency graph might look like. This is a directed graph, but it's not necessarily acyclic. So what we do is we find the maximal strongly connected components. And the graph where these maximal strongly connected components are now super nodes is a DAG, so we can sort it topologically and then execute the strongly connected components in inverse topological order. For those that have more than 1 command, we execute the commands in increasing order of their approximate sequence number. And this is an extra ordering constraint that I haven't described, but a simple way to think about it is essentially a Lamport clock. So what this all gets us is the following properties. First of all, linearizability. If 2 commands A and B interfere, and A is committed at some replica before B is proposed to any replica, then A will be consistently executed before B. This is a strong consistency property. And the second one is the fast path quorum, which is how many acceptors, how many replicas have to agree on a certain set of dependencies for that command to be committed on the fast path, is F plus F over 2, where F is the maximum number of tolerated failures. And it turns out that this is optimal for the most common deployments of Paxos, 3 and 5 replicas. And it's always better than fast and generalized Paxos by exactly 1 replica. What this means in practical terms is that if we do geo-replication and we have a replica in Japan, 2 on US West Coast, 1 on the US East Coast, and 1 in Europe, a replica in Japan can commit a command after just talking to its closest neighbors, which is the replicas on US West. It doesn't have to go all the way to Europe or to US East. Okay, so now the results. We've implemented EPaxos, Menzies, generalized Paxos, and Multi-Paxos in Go. And we tested these protocols. We compared them on Amazon EC2. The workload is a replicated key value store. So this is the same map that I showed you before. We have a replica in Virginia, 1 in North California, Oregon, Ireland, and Tokyo. And this is to give you a sense of the round trips between these locations. So we had clients at each of these locations, and the clients submitted commands, and then they measured the time it took to get back the commit notification for all the 4 protocols. So an EPaxos client in California only has to wait for its local replica to talk to its closest neighbors. its two closest neighbors, which are Oregon and Virginia. And that's true also for a client of Multi-Paxos, but only because the Multi-Paxos leader in this experiment is in California. For a client in Virginia, it has to first go to the leader in California, wait for the leader to commit that command, and then get back to the client in Virginia. So it takes almost twice the latency that an EPaxos client at the same location would experience. Mencius is slower because it has to wait for information from every replica in the system before it can commit a command. And generalized Paxos is slower because its fastpath quorums are larger. It has to wait for the third closest replica to reply instead of the second closest replica. And in fact, at every location, EPaxos has the smallest latency of all the protocols. And that's because EPaxos has optimal commit latency in the wide area for 3 and 5 replicas. Now, of course, when commands interfere, the commit latency of EPaxos doubles. But we believe that to be rare enough that it affects at most the 99th percentile of operations. And furthermore, it's fairly easy to mitigate. OK, so now in a local area cluster, these are throughput results for small commands, 16-byte commands. We compare Multi-Paxos, Mencius, and EPaxos for various rates of command interference. 0% means that no commands interfere. 100% means that all commands interfere. And what you can see here is that EPaxos has higher throughput than Multi-Paxos and Mencius when command interference is low, which we believe to be the realistic scenario. Furthermore, when a replica is slow, in our experiments, one of the replicas experienced high contention for its CPU. The throughput, the performance of EPaxos degrades much more gracefully because we have the flexibility to avoid a minority of replicas that are slow. Our intuition might tell us that Multi-Paxos, which has a single leader, might be better with batching. Batching is a common optimization for throughput. The reason why we might believe that Multi-Paxos might be better with batching is because it has the ability to take all the commands and commit them in one large batch, whereas EPaxos and Mencius will have to commit multiple batches, right, for the same number of commands because every replica gets commands. This is a latency versus throughput graph. Lower and to the right is better. This is Multi-Paxos. EPaxos is the red line. Turns out that EPaxos has about 3 times higher throughput and about an order of magnitude lower latency at peak. And perhaps surprisingly, EPaxos 100% is almost as good. And the reason is the extra cost of the second round of communication is amortized across the large number of commands in a batch. Because second round messages are small, they don't have to contain the commands themselves again. The reason why EPaxos is better than Multi-Paxos is because the load of communicating with the clients is distributed across all the replicas in the system instead of falling squarely on the Multi-Paxos leader. And the final set of results that I'm going to show you is this nice side benefit that we get with EPaxos, which is constant availability. This is a throughput over time graph, which shows what happens when the Multi-Paxos leader fails. When it fails, the system throughput goes down to 0 because no command can be committed until a new leader is elected. In Mencius, when any replica fails, the same thing happens. The throughput goes to 0. In Mencius, however, commands can be processed up to the point where they should be committed. After a grace period, one of the live replicas in Mencius succeeds in committing no ops on behalf of the failed replica. And the spike that you see on the graph is those delayed commits. No such problem in EPaxos, because in EPaxos we have the flexibility to avoid a minority of failed replicas. So to conclude, I'm going to point out some of the main insights in EPaxos. The main one, the most important one, is that dealing with order explicitly gives us great benefits. First of all, it gives us high throughput because we can balance load evenly across all replicas. It gives us better performance stability because we can avoid replicas that are slow. And because of the same reason, we can avoid replicas that are far away, so it gives us low latency. But it also allows us to do the following optimization. Optimize away only the delays that matter. Previous Paxos variants that optimized for low latency, like fast Paxos and generalized Paxos, they optimized away the latency or the message delay between the client and the first replica. Now, in the wide area, clients are usually co-located with their closest replica, so this delay is insignificant. Instead, by not focusing on this, we instead can focus on making fast path quorum smaller, which in turn gives us the nice low latency benefit. And I will leave you with this slide with pointers to tech report with a formal proof of correctness for EPaxos, along with a model checkable TLA plus specification, and a pointer to our open source release of the comparison framework that implements EPaxos, Multi-Paxos, generalized Paxos, and Menzies. Thanks.
Marcos Aguilera, Microsoft Research. So you mentioned at the beginning that Paxos doesn't require a failure detector, but it's not quite accurate, right? It requires the omega failure detector, because after all, otherwise it would violate the FLP result. But what I wanted to ask you is, what is the assumption that you're making in your EPaxos protocol that allows you to solve consensus in a synchronous system? You must be assuming some failure detector or some form of partial synchrony or something else. So what is it?
So what I meant by that slide was that we don't actually have to declare failure of any minority of replicas to be able to continue processing commands. Okay. Sorry, I guess I didn't understand the second part of your question.
What is the assumption that you make in EPaxos that allows you to solve consensus?
It's the same as in Paxos.
Okay, so it's the omega failure detector.
I mean, we don't change the consensus problem from Paxos, no.
Thanks.
Hi, Rich Draves from Microsoft. You said that with EPaxos, if you kind of get unlucky with interference, you could have a second round trip. And as I was thinking about it, it seemed like if you got unlucky in your second round trip, sort of continued interference, maybe a third round trip or more round trips could be required. Is that not the case?
No. It's 2 round trips at most, because the second set of, or the dependency constraints in the second round, they don't have to be updated by the acceptors. The acceptors only have to acknowledge. So no one has to update them, and no one does.
I have an example I want to review with you then afterwards.
Okay, great.
So a question from the moderator. So the Paxos is a consensus protocol, and inherently there's no notion of leader. You can surely use multiple instances of consensus to decide the ordering of operation. Can you further clarify the premise of the paper?
Yeah, so I mean, as I showed in one of the slides, indeed in Paxos, all replicas contend for a pre-ordered sequence slot, a sequence space. So unfortunately, in Paxos, the problem is that to get a command committed, it takes 2 round trips. Now, to solve this problem, the fact that it takes 2 round trips to commit a command, we ideally would like to take only 1 round trip. Practical implementations of Paxos actually use Multi-Paxos. In Multi-Paxos, there's only 1 replica that actually proposes these commands.
So the second question is the procedure necessary to execute a request, detecting and sorting dependencies seems quite extensive. How do you keep this procedure small, and how does this impact request latencies when several requests are pending, such as after crashes?
Yeah, so the ordering procedure is not actually that extensive. It's just an algorithm for finding and storing components that's linear in the number of edges, which turns out that in practice it's linear in the number of nodes in the graph, because most of the times interference is transitive, which means that the number of edges is linear in the number of nodes. And the number of nodes in a dependency graph is usually small. because of two reasons. One is that we execute commands as we commit them. So the the committed unexecuted command list never gets too large. And also, it depends on the interference rate. And if the interference rate is small, these graphs are never going to be very large.